Hello and welcome to discussion 9 of X370. So today we're going to cover the pipeline control hazard. The first part is about the overview of control hazard. Why will we have this hazard? And next we will talk about how to resolve this control hazard. And we might want to improve the performance while we resolving the hazard. So this is about the branch prediction and how we calculate the performance. So BEQ might be problematic in the pipeline. So in the single cycle or multi-cycle data path, we cannot execute more than one instruction at the same time. But in pipeline, we can execute 5 instructions in the same hardware. So in single cycle or multi-cycle data path, the next instruction after BEQ is executed after we know the result of BEQ. Like we know the branch target and the comparison result of the BEQ. However, in the pipeline, we have 3 instructions being fetched into pipeline before we resolve the BEQ. Like before we knowing which instruction we need to execute next after BEQ, we already executed 3 instructions. So this is problematic for the pipeline. And we need to fix this using the similar hazard detection as we do in the data hazard. So similar to the data hazard, we will have 3 different methods. First one is using the avoidance, like avoid using BEQ. Like this is not a good way, but we can try to avoid the BEQ. And another alternative approach is we can delay this BEQ. We can have a new instruction called delayed BEQ. And this delayed BEQ will execute it 3 cycles later. So the 3 cycles, like the 3 instructions after this delayed BEQ, we will execute them no matter the branch is taken or not taken. So it can be used like this. We have a delayed BEQ and instruction A, B, and C. So these 3 instructions will be executed no matter the branch is taken or not taken. Like these 3 instructions doesn't depend on the BEQ. So, and sometimes if we don't have 3 instructions, we will just add no ops. We'll just add 3 no ops after this delay BEQ. So this instruction D here, this instruction will depend on the delayed BEQ. Like if the branch is taken, we may not execute instruction D. However, this is also changing the assembly code or changing our instruction set. So if we have a new pipeline or new processors, the old code may not be able to run, and this is not a good way to do it. But let's still see an example of delayed BEQ. This is a normal BEQ, like we just branch at the next instruction after the BEQ. Let's see how we can change it to delayed BEQ so the hazard can be resolved. The instruction before the BEQ will be executed no matter what. So we will just change the order of these instructions. So we move around the BEQ. We have the delayed BEQ. And we will have the add instruction and NOR instruction. So this 2 instruction gets moved below the delayed BEQ, and delayed BEQ will execute it 3 instructions later, and we need 1 more. So we add a no op. The no op can be added here or here, so it doesn't matter. And after these 3 instructions, the delayed BQ will be executed. And we can have the code, which depends on the branch. So basically, it's move the instruction around and change the order of them. And one thing for the delayed BQ is the register here cannot have any data dependency on the instruction before it. And this is like the condition we can move around. So if one of these register is maybe, let's say this is 1. So we can only move the NOR after the BQ because the register here will depend on the first add instruction. There cannot be data dependency for these 3 instructions. So rearrange the code and we can fix the control header. But usually, like, changing the assembly language is not what we want. We want to modify our hardware a little bit so it can support all the assembly code we originally have. So this is why we have the second method, detect and stall. So in the decode stage, in the control ROM, we can know the opcode and whether this is a BQ instruction or not. If this is a BQ instruction, we will stall the PC and insert one no-op into RFID pipeline. In this cycle, we won't increment PC, and we have a one no-op in the RFID pipeline. So this is a one BQ in the ID stage. And in the next cycle, when BQ comes into the EX stage, here, we still don't allow PC to increment, and we insert one no-op. So every time the stall, just don't increment PC and insert So the first no-op we inserted is moved from RFID pipeline to IDEX pipeline. And we can insert the second no-op into RFID pipeline. So this is the EX stage for BEQ. And next cycles, when BEQ is in the memory stage, here we will update PC. Because ALU is in the EX stage, and ALU will compare the value into registers. And we calculate the branch target, the PC plus 1 plus offset in this adder in the EX stage. So when BQ is in MEM stage, we have the branch target and we have the result for comparison. So now we can update PC. But we don't fetch the instruction in the same cycle. So don't fetch the instruction. We only update the PC, and we insert no op to RFID. So this is the third no ops. Here are the 3 red boxes. These are no ops. And this is how we do detect and stall. This is very slow and the performance is not good because every time we have a BEQ instruction, we will introduce 3 extra cycles. And if we have a lot of branches, like we have a lot of for loop or if else statements in our code, this will run very slow and we don't want it. So we can also draw the pipe trace for the detect and stall method. You can first draw on yourself and then we can go through these questions. So just pause here if you want to do it. And we can go through this problem. So this is a BQ, and after the instruction after the BQ needs to be stalled. And instruction before the BQ will not be affected. So the add and or this will be IFID X right back. There's no data header in this code, so we don't need to consider about data header. And these are just 3 instructions. And for the next add instruction, we will stall it for 3 cycles. So this is a first stall, second stall, third stall. And after these 3 cycles, add is in the IF stage. So this is when BQ actually is in the write back stage. When BQ in the mem stage, we don't fetch the instruction. And in the next cycle, when BQ moves to the write back stage, like we have 3 no ops. We will fetch our new instructions. So when BQ in the write back stage, we just line up these 2. We fetch the new instructions. And yeah, so this is a pipe trace for using detect and stall. So we are trying to improve the performance, and we may not want to stall for every BQ instructions because some of them might not be taken. We can just fetch the next instructions after the BQ if the BQ is not taken. So this is why we want the speculate and squash solution. We will predict whether this BQ will be taken or not taken and continue to fetch the instruction into the pipeline based on our guess. So when the branch is resolved in the mem stage, this is where we actually know whether we need to take branch or not. So if our prediction is correct, there are no penalties because we have all the instruction into our pipeline and we just go next. So the 3 extra cycles are only added when our prediction is wrong. So in mem stage, like we have instruction A, B, and C into our pipeline. And if our prediction is incorrect, we will just change these 3 to no ops. Like in the IFID and EX stage, we haven't modified any memory or modifying any registers, so we can just change the instruction into no op and it will not execute it after that. So how do we do the predictions? Basically, we need 3 things before doing the prediction. First is whether the instruction is a branch. This is in the IF stage. The prediction is in the IF stage because we will update PC when BQ is in the IF stage. So first, knowing the instruction before decoding, and next is predict the branch will be taken or not taken. So this is like a Boolean variable. Do we need to take branch or we just go to the next instruction? The third thing is where the branch will jump to. So this is a target. And this is PC plus 1 plus offset. the adder for calculating the target is in the EX stage, but we need some way to know the target in the IF stage so that we can update the IF stage. So if we don't know any of them, we will not predict the branches taken. Yeah, so next part is about the branch predictor. So branch predictor is used to solve these three questions. The first part of the branch prediction, like there are two parts. This needs to be worked together to get the prediction. So the first part is a target predictor. This will tells you the target PC and tells if the instruction is a branch before the decoding. And the hardware to implement is called BTB, the branch target buffer. So we will have the PC for the BEQ. And you can just imagine the target buffer as some black box, and the BTB will tells you whether this is a BEQ instruction and the target. So this is a black box. This will give you the BEQ or not and the target. And the second part is direction predictor. This is we predict taken or not taken. Just a Boolean variable tells the PC which value to use next. And I think next we will focus on the direction prediction. Taken or not taken. So the static direction predictors, usually we have these three types. First is always not taken, and this is what we implement in our project. In project 3, we always predict branch will never be taken. So that means we just continue fetching the next instruction. Because if the branch is not taken, we will fetch the next instructions. We don't need to resolve the branch in the IF stage. And the second one is predict always taken. So we will predict this branch will always taken. The next instruction we fetch into the pipeline will always be the branch target. And the third type is backwards taken, forward not taken. So this is very useful when we have a for loop. Here we will have some for loop condition, so we will use BEQ. And at the end of for loop, we'll just have the BEQ maybe some 0, 0 back, or just go back to the for loop and check condition again. So you can see these are all zeros. So this instruction will always execute it. Like we'll always take branch if we execute these instructions. So this is a backwards because we are going back, and we will predict this always taken. And we will have 100% accuracy for the BQ going back like this. And for this BQ, this will break the loop. So it's going forward, jumping to somewhere after the for loop. And our prediction is not taken. Like this only taken once when the condition is not satisfied. So we will predict not taken. And this prediction can all be done at compiling time. So we do not modify anything in the execution time, like runtime. Another type is dynamic predictors. So this will be changing in the runtime. And it will take advantage of the last prediction or the result of the last branch instruction. So this is a finite state machine, and we will have some initial state. So maybe we initialize to not taken, or we can also initialize to taken. Let's say we initialize to branch not taken, predict not taken state. So here, our output is not taken. So we predict the branch is not taken, and we just continue to fetch the next instruction. And when BQ is in mem stage, we will know whether the branch is taken or not. If the branch is actually not taken, which means our prediction is correct, so next time we will still predict not taken because we are correct. And if the branch is taken, we go to the next state. So this time we are wrong. Next time we will predict taken. So here's the prediction just based on the last time, the result of the last BEQ. And we can have a more complicated branch predictor, the 2-bit branch predictors. So this will increase the accuracy for the branch sequence like this. Taken, not taken, taken, not taken. So if initially we predict not taken, like this is prediction. This is predict not taken. And if we are incorrect, we will change our prediction and we are incorrect again. So we just keep changing every time and we have 0% accuracy for the sequence like this. So if we want to do better, we will have another branch predictor, a 2-bit branch predictors. So 2-bit will give you 4 states. Here we will say this part, like this is like usually we say it's a strongly taken. Yeah, it's already there. So this is strongly taken state. So in the strongly taken states, our prediction is taken. And if we are correct, like the branch is actually taken, we will stay in the same state. So we will predict taken next time and we still say it's strongly taken. And if we are wrong this time, we will change to another state called weakly taken. So in the weakly taken state, it's also taken. So taken is a prediction for these two states, the output or the prediction. So output taken. And if we are incorrect again, which means we have predict wrong twice, so we will go to the weakly not taken state. So here the output is not taken. The output is not taken. And if we are correct this time, we will go to the strongly not taken. So it's like if our branch is taken, we will gradually move to the strongly taken state. From the strongly not taken, gradually move to the strongly taken. So if the branch is keep not taken, we will just move to this side. Finally, we will go to the strongly not taken state. And this is a 2-bit branch predictor. So if you have any questions, feel free to ask on Piazza or come to office hour. The last part is how we analyze the performance of the different method and how we can improve it. So let's just do an example. Assume we have 1,000 instructions. 35% are LW, and 30% of which are followed by a dependent instruction. So this means we have a data hazard. %10 are SW, 25 is add or NOR, 30% are BQ, and 60% of which are taken. So the first question is, what is the CPI of our pipeline, assuming we are using the data forwarding for data header and speculate and squash for control header. It's predict not taken. So the CPI here is number of cycles divided by number of instructions. So number of cycles basically will have several parts. So first is the number of instructions plus 4. This 4 is we use to warm up the pipeline. So after the fifth cycle of the pipeline, each cycle we complete 1 instructions. So it's number of instructions plus 4 plus the penalty for data header. So if we are using data forwarding, only the dependency for a LW instruction will insert 1 no-op. So we have 35% of LW and 30% have the dependency, and totally we will have 1,000 instructions. So this is the data header inserted for LW instruction. And next is a control header. So control header is for BEQ, and because we are using the predict not taken, so there are only 3 no-ops if our prediction is wrong. Like we only have penalty if the prediction is wrong. So prediction is not taken. So when the branch is taken, the prediction is wrong. So 60% we are wrong, and we have 30% of BEQ. And each of them have the 3 cycle penalty, and we have 1,000 instructions in total. So this will give you the number of cycles we have. And this is a CPI. So for the same code, like the same benchmark, if we are still using the data forwarding, but we are using detect and stall, what is the CPI here? So CPI is still number of cycles divided by number of instructions. And number of cycles, the warm-up part will not change, and number of instructions will not change. And the data header part, we are still using the data forwarding. So we still have 35%, 30%, and 1,000 instructions. So this is a data header. But here, the control header, we are using detect and stall. So this is insert 3 no-ops for every BEQ instructions. We have 30% of BEQ and 1,000 instructions in total. And each of them needs 3 extra cycles. So this is for the control header. And we can get the number of cycles when using the detect and stall. And the CPI is 2.009. This is higher than our first solution. Yeah, so this is the end of today's discussion. Thank you for watching.